We are now in the mathematical portion of Lecture 2 on the course Mobile Sources Air Toxic Risk Assessment. We're going to create a small model based on uncongested roads. The next segment of this lecture will be on congested roads. So under congested roads, the spacing between vehicles is an important variable. And we have a model that approximates this spacing between the vehicles. It will be defined by an exponential distribution. And we will call that an exponential PDF, probability density function. So I'll put a comment here so I describe what I mean. And show probability density function, PDF. And this probability density function will be defined by a mean, we'll call it mu, and it will also be defined by a sigma, which is the standard deviation. So this exponential function that describes spacing between the vehicles will be a function of x, which is equals to 1 divided by mu times the exponential of the x by mu. That's it. So how would we implement this? What we're going to do now is describe first how to define the mean. And the mean is equal to the vehicles on 1,000 meters. So it is defined by 1,000 meters, 1 kilometer of road, defined by the density of the vehicle. And we know that the density of the vehicles, if they are between 0 and 20 vehicles, we have uncongested roads. If we have D between 20 and 40, this is near capacity. We know we drive and we know there are certain areas where there's a lot of cars, but it still flows fairly well. And if it is above 40, we're under congested road situations. So be D bigger than 40. This would be congested. I should also remind you that if D bigger than 60, then what we have is, I'll call it the parking lot where all the cars are basically just stuck there, not going anywhere. So in our model then, what we're going to do is basically, we're going to define x as we did before, equals, and p dot lin space from basically 0 to 30. I want 100 elements here. And let me import then the libraries for SNP. And I will import the plotting library. Import plot SPLT. We adopt that as a standard. And here we're going to say that mu, the average, equals, let's say 20 vehicles, 1,000 meters. So we could say less congested. I'll just say it is 5. Then we have, I'll call it y equals, and we will define the equation, which is basically 1 divided by mu, 1 divided by mu times p dot exp, the exponential, the x that we created, divided by mu. Let's plot this and see what we got. So we're going to do plt dot plot x comma y. We already learned this. Plt dot show. Going to run. It's a vast library set. And here's the distribution. Again, I have nothing for the information on the x-axis here, the title, and the y-axis. Now we'll teach this following segment here on this example, because I want you to understand why we're plotting. There are two main reasons. The first one, we want to see how a function changes when the independent variable changes, how it responds to that change in the variable. So if it is in the x-axis, how will the curve change? How is the function changing? The y-axis responding to the changes in x. So we just saw this, but we also use these plots to compare different functions. So we need to be able to plot in a single graph two types of curves, or two different curves, or three different curves. So how do we do this? Well, let's say that this case, we're going to call this y1, and we're going to create a second variable, a second curve, using mu equals 10, no longer 5. We're going to say y2 equals the same function here. Now we're going to plot both of them. So what we can do here is, this will be y1, and now I do x, comma, y2. Let me show you this. I have two curves, so we do not know which one is which. I could have done this here in another way. I could have and you can see here that I have the same results. So we're going to use together here. I can do the following. I can say that this first one with the mean at 5, I'll say it is red line. And this other one, I'm going to say it is a blue line. So now we can distinguish which function is which. Now I know that the red is with the average, the mean, a red line, and the mean with equals 10 is the blue line. But if I give this plot to somebody, they will not know. That's why we need to take note. So we're going to do what we did before. PLT dot X label. This will be X. PLT dot Y label. This is the exponential PDF. I'm going to PLT dot title, and we say changes in mu 5 to 10, for example. We already know what we're going to get here. It's a plot. Now I have knowledge of what this means. It would be nice if I could describe these curves here. Now what we are going to do is this. I'm going to say label equals mu equals 5. Here we're going to say label equals mu equals 10. Now I have to do plt.legend. I can have parameters passing here. We're doing the simplest possible explanation for us to reach our objectives, and I will not spend time with that. So now we know that the red mu equals 5, mu equals 10. Let's say this is black and white. We will not be able to distinguish. So what I'm going to do is on the blue, or I can also do a different plot instead of a straight line. And we can indicate where the mu equals 10 is being plotted and where mu equals 5 is being plotted, even though we have black and white printers. This will conclude our first segment on the math part of representing the spacing between vehicles on an uncongested road. Thank you very much.